In this chapter, we will discuss how to handle both input and output in Java. Input refers to information that is provided to the program which will use it during its processing. Output refers to information that the program provides to the outside world. Both input and output can be stored in various formats. In this chapter, we will primarily focus on the usage of files for this purpose. Let's have a look at the overview. We will kick off by providing a recap on the basic principles of input and output. We will then elaborate on both concepts from a Java perspective. Next, we will zoom into streams and scanners, two key concepts to work with input and output in Java. This will be followed by a discussion on input and output from the command line. The chapter will conclude by reviewing input and output from files. The output of a program can be delivered in various ways. Popular examples are to a monitor, printer, file, or even to other programs. Likewise, the input for a program can be received from the keyboard, mouse, a file, or also other programs. As mentioned, in this chapter, we will focus on file I/O, whereby both input and output are stored in files. Before we continue the discussion, we need to introduce two important concepts: file modes and the difference between text and binary files. Let's start with file modes. A mode refers to the way a file can be used by a program for either input or output. Here you can see some popular modes listed together with their abbreviations, as they are common in most programming languages. Let's review some of them. R refers to opening a file for reading only, whereby the reading pointer will be positioned at the beginning of the file. R+ refers to opening a file for both reading and writing. W refers to opening a file for writing only, whereas W+ allows the file to be both read and written. A refers to opening a file for writing only, whereby new data is appended at the end of the file. This can be further extended as A+, which will also allow to read the file. In both cases, the reading pointer will be positioned at the end of the file. X will create a file and open it for writing only. It will fail if the file already exists. This can be further extended as X+, which will also allow to read the file. C and C+ allow to open a file for writing only, or for reading and writing, whereby a new file will be created in case it does not exist yet. The second important concept concerns the difference between text and binary files. This relates to how the file encodes the data it contains. Both files store data as a series of zeros and ones or bits. However, for a text file, the bits represent characters, while in a binary file, the bits represent custom data, stored and interpreted according to a particular format. When you create a TXT file in Windows Notepad, you are creating a text file. Here, you can see an example of this. To the left, we have a text file with some text. To the right, you can see this file in its hexadecimal representation, which is a compact representation of the bits stored in the file. Every 2 hexadecimal characters map to a byte or 8 bits, which corresponds to exactly 1 character. For example, 55 maps to capital T, whereas 73 maps to S. Binary files are less structured in the sense that they contain a sequence of bits that are structured and organized according to the program or programmer who created the file. Depending upon the content of the file, standards may be adopted. A popular example is JPEG for image files. To the left, you can see a JPEG image of the front cover of our Java book. In the middle, you can see the corresponding raw bytes in hexadecimal notation. As you can see to the right, the contents of this binary file cannot be represented as a series of characters in a meaningful way. Let's now have a closer look at input and output in Java. Java I/O is based upon the concept of a stream. A stream is an abstraction of a particular input source or output destination. More specifically, it can represent files, a program console, other programs, memory locations, or even hardware devices. Depending on the source or destination, it can support various data formats, such as raw bits and bytes, characters, primitive data types, and even complete objects. A stream basically represents a sequence of data and offers a unified model to deal with I/O. Let's provide some more detail. Here you can see the concept of a stream once more illustrated. A program can make use of various input and output streams, which are in turn connected to various sources or destinations. This also clarifies why you will typically not deal with file modes in Java, as the type of stream, input or output, will determine whether you want to use a file as a data source or destination. In what follows, we will discuss various types of streams, such as byte streams, character streams, buffered streams, data and object streams, as well as some other very specific streams. As the term suggests, a byte stream is a sequence of data represented as bytes. Remember, a byte corresponds to 8 bits. A byte stream is the lowest level of I/O in Java, so that all other streams are built on them. All byte streams subclass input stream and output stream, both with their own methods. Let's have a closer look. Here you can see some key methods for input stream. The method read reads the next byte of data from the input stream. It returns -1 if the end of the stream is reached. The second method reads some number of bytes from the input stream and stores them into the array B. It returns the total number of bytes read into the buffer, or -1 if there is no more data because the end of the stream has been reached. It can also be extended with an off and length parameter, as the third method illustrates. This method reads up to len bytes of data from the input stream at offset off into an array B. It returns the total number of bytes read into buffer, or -1 if there is no more data because the end of the stream has been reached. The skip method skips over and discards n bytes of data from the input stream. It returns the actual number of bytes skipped. The close method closes the stream and releases any system resources associated with it. You can see some other methods also listed. Here you can see some key methods for output stream. The first method writes the specified byte, represented as an int variable, to the output stream. The second method writes the specified byte array B to the output stream. The third method writes len bytes from the byte array B starting at offset off to the output stream. The close method closes the output stream and releases any system resources associated with it. The flush method flushes the output stream. In other words, it forces any buffered output bytes to be written out. Keeping unused streams open can lead to resource leaks or memory problems. Hence, it is important that both input and output streams are properly closed using the close method once you are finished using them. You can see a first example of using input and output streams. Our Java program illustrates how to copy a file using both streams. We start by importing file input stream, file output stream, and I/O exception from the java.io package. File input stream will be used to open the file groceries.txt. File output stream will be used to write to the file groceries copy.txt. If this file does not exist, its creation will be attempted. If the file does exist, its content will be overwritten, unless we would have passed true as the second argument of the file output stream constructor. We then use a while loop to keep reading the original file until we reach the end, in which case the read method will return -1. Inside the loop, we use the write method of file output stream to write the read byte to the new file. We also show the contents on the console as it is copied. To successfully do so, we cast the integer to a character. An I/O exception is caught in case errors occur, such as when the original file does not exist. A finally block then closes both streams. The previous example can be reworked using try with resources as we discussed in Chapter 6. Remember, a try with resources is a try statement that declares one or more resources, such as streams in our case. These resources will be automatically closed at the end of the code included in the try block. As such, our code becomes as illustrated here. You can see that we no longer have to explicitly close both streams. The print stream class is another interesting example that implements extra methods to allow for easy output formatting on top of a normal byte output stream. Some popular methods are listed here. The first method writes the specified string to the print stream. Other primitive types such as char, double, int, etc. can also be accepted. The second method writes the specified string to the print stream, but also terminates the line, or in other words, adds a new line. You can also accept char, double, int, etc. The format method takes the format string as its first argument and the variables you want to format as the following arguments. The format string contains a number of percentage fields representing where, which, and how variables should be formatted. Note that the system.out object we have been using to send output to the console is in fact an example of a print stream. It is open at the start of your program and closed automatically at the end, so you can use it directly without further management. Here you can see an example of using a print stream object. In this example, we are using system.out as a print stream object. Since print stream is a subclass of output stream, it also implements the write method, which works with bytes, remember. The method system.out.write50 prints the byte 50, which is represented as an int and corresponds to character 2. A new line character is then added by casting \n to int. The workings of the print and println methods should be fairly straightforward. Note the use of \n, \r, \t, and double backslash within the strings to insert special characters. These special backslash combinations are called escape characters. The class concludes with 2 illustrations of the format method. Character streams translate Unicode characters, as they are used within Java, to and from the characters locally specified. In other words, they are equivalent to byte streams but adapt to the local character set. Reader and writer are two examples of classes implementing character streams. File reader is a subclass of reader and implements a character stream to read files. File writer is a subclass of writer and implements a character stream to write files. Let's work out an example. Here you can see our earlier file copying example, but now worked out using character streams. We are now using the file reader and file writer classes here to open the original file as a data source and a new file as a destination. If the file does not exist, the program will attempt to create it. If the file does exist, its content is overwritten unless you pass true as the second argument of the file writer constructor. The rest of the program is performed very similarly to using byte streams. Note that we are using a try with resources block to handle the closing of the reader and the writer automatically. Most streams in Java are unbuffered, which implies that each write and read request is handled directly by the operating system. This makes programs less efficient, as every write request to a file will trigger disk access. Buffered streams are wrapped around other streams. They provide a dedicated space in memory, called a buffer, to store data in an efficient manner. They will only request time-expensive operations if necessary, such as when the buffer is full. 4 buffer classes exist, which can be wrapped around a byte or character input-output stream: buffered input stream, buffered output stream, buffered reader, and buffered writer. Here you can see our file copier example revisited with buffered streams. We are now using buffered reader and buffered writer classes to open the original file as a data source and a new file as the destination. Note that these classes wrap around normal reader and writer classes, or in our case, file reader and file writer. The rest of the program now reads data line by line. Note that the new line terminator will be stripped from the red line, so we use system.line_separator to add a platform-dependent line ending when writing the line to the output file. Note also that the readLine method returns null when the end of a stream is reached. Data streams support binary input and output of primitive data types such as Boolean, char, byte, short, int, long, float, and double, as well as string values. All data streams implement either the data input interface or the data output interface, such as data input stream and data output stream. These streams are subclasses of input stream and output stream and are thus a specialization of byte streams. Object streams are similar to data streams, but allow the serialization of all objects that implement the serializable marker interface. Object streams implement either the object input or object output interfaces, which themselves are subinterfaces of data input and data output. Examples are object input stream and object output stream. They are also subclasses of input stream and output stream and are thus a specialization of byte streams. Let's work out an example. In this example, we create a small class to illustrate the workings of an object output stream. Note that an object output stream can both write primitive data types as well as serialize objects. The object output stream class is created as a wrapper around a normal file output stream. Next, object output stream exposes a number of methods such as writeInt, writeDouble, and so on to write data to the stream. Although you save the data to a file named saved.txt, the reality is that you are creating a binary file and not a text file, which explains why the text looks all garbled when you try to open it with a text editor. You are looking at raw binary data representing primitive values and objects stored according to the format defined by the Java virtual machine. Various other streams exist. Examples are audio input stream, which reads in audio-based data, and zip output stream, which implements an output stream for writing zip or compressed files. Most of these other streams are byte streams and subclasses of input stream or output stream. As we already discussed, if your input data is binary, you can use data or object streams to read in everything correctly. If your data is given as text, we have seen how the BufferedReader class can help read the data line by line. But what if a line contains different fragments you want to appropriately parse? You can see an example here of a file groceries with prices.txt, which contains both the name of the item purchased as well as the price. Java provides a simple means to break down input into various fragments, or tokens as they are called, and translate them according to their data type. The class that helps you do this is the scanner class, and found as java.util.scanner. Let's provide an example. Here we have a class showGroceries. A BufferedReader object is created and connected to the file groceries with prices.txt. As previously, the BufferedReader object is then read line by line. Every line is then parsed into an item and price by splitting it up where the comma occurs. Although this works fine here, you might want to resort to using a scanner object instead. Here you can see the same example, but now with a scanner object. The scanner class wraps around a BufferedReader class in this example, but can also be directly applied to a string if desired. Next, we set the delimiter pattern of the scanner. A delimiter is a piece of string by which we want to split up text fragments. By default, the delimiter of a scanner equals all white space characters, such as a new line, a space, or a tab. In our case, we change it to match either a comma followed by a space or a new line. Note that we use the pattern class here to supply a regular expression, a relatively advanced format that specifies text patterns. We also set the locale of the scanner object to English to make sure the decimal prices are read in and interpreted correctly. Locale is a Java-provided class to represent geographical regions. Instead of instantiating a new object, the class provides a series of static members that can be accessed and used directly, such as locale.english or locale.korea. Next, a while loop is iterated as long as the scanner is able to feed text fragments. If this is the case, we know we can immediately read in two pieces of fragments at once, the item and the price, using the next and next double method. In this section, we will illustrate how to use the comment line for input and output. Although most applications these days use graphical user interfaces or GUIs, which we will discuss later, this has not always been the case. Here, you can see the comment line in Microsoft Windows. It can be asked for using the cmd.exe command. In every consola or command line application, three mechanisms exist to communicate with the user. In Java, these are implemented as the standard streams corresponding to the following: system.in, which represents a byte input stream to take user input; system.error, which is a print stream to output error messages; and system.out, which is a print stream to output normal messages. You can use these streams just as you would use normal Java streams, with the difference, however, that you don't need to open or close them. Here you can see an example of this. System.in, system.out, and system.error all act as normal streams as we discussed before. Note, however, the use of the input stream reader class to make a bridge from system.in, which is a byte stream, to a buffet reader, which is a character stream. We use buffet reader instead of buffered input stream because we want to use the readLine method to read in a complete line of user input. We can also make use of a scanner object instead. You can see this illustrated here. The scanner object can be directly defined based upon system.in. As an alternative, we can also make use of the class consola. This class lives under java.io.consola and can be accessed as system.consola. A consola object provides all features that standard streams have, as well as some other features such as secure input mechanisms, which can be useful for password entry. The consola also provides input and output streams that are character streams. You can see an example of using the consola class here in our class getPassword, which asks for username and password. The first part of the main method verifies if a consola object can be created, since not all operating systems support this. Note that you cannot execute this program in Eclipse, as Eclipse does not provide a so-called interactive command line. You will need to export this class as a runnable jar file and then execute it from the command line of your operating system. You can see this illustrated here. Note that thanks to the readPassword method, the characters you type for the password will not appear on the screen so as to guarantee its confidentiality. In what follows, we will further zoom into input and output from files. We will hereby discuss both Java and IO2 and legacy file input and output. Java 7 introduced the NIO2 API to offer a new file system API. Note, however, that existing legacy file I/O methods remain supported. In what follows, we will start by reviewing the NIO2 API for working with files. Two key concepts are the path interface and the files class. Let's get into some more detail. A path specifies the access path to a directory or file. An example could be C, projects, Java, book, bmi.class, which clearly indicates how to navigate to the file bmi.class. The Java path interface is part of the java.nio.file package. Paths is a normal Java class which implements the path interface. Path objects contain a file name and directory list used to build the path and can be used to examine and work with files. Creating a path is done by using the get method on the paths class as follows. Path mypath equals paths.get cprojects outline.txt. Here you can see some example methods that can be called on path objects. The toString method returns the string representation of the path object. The getFileName method returns the file name or last element of the path object. The getName int I method returns the path element corresponding to the specified index I. The getNameCount method returns the number of elements in the path. The subpath int I int j method returns the subsequence of the path as specified by the beginning index I and ending index j. The getParent method returns the path of the parent directory of this path. The getRoot method returns the root of the path. The normalized method cleans up redundancies from a path and returns the clean result. Apart from the path interface, the files class is the other most important class contained in the java.nio.file package. This class offers a set of static methods for reading, writing, and manipulating files and folders. Here you can see some example methods listed. Both the exists and non-exist methods check whether a path exists. The isReadable, isWritable, and executable methods check whether a path is readable, writable, or executable. The isDirectory method checks whether a path represents a directory, whereas the isDirectory method checks whether a file represents a directory, whereas the isSameFile method checks whether two paths resolve to the same location. The next operation you can perform using the files class is deletion. You can see this illustrated here. It is possible to delete both files and folders, but for folders, the folder needs to be empty before it can be deleted, otherwise an exception will be thrown. Note that there is also a files.delete if exists method. This method works in a similar manner, but will not throw an exception when the file does not exist. It just does nothing in that case. Obviously, also copying and moving files is supported. The copy method allows to copy a source file to a target file, whereas the move method allows to move a source file to a target file. Note how these methods provide a more straightforward means to copy and move files compared to the stream-based file copy programs we have discussed earlier. This is one of the nice improvements of the NIO2 API. Let's now also take a look at how to read, write, and create files using the NIO2 API. The readAllBytes method reads all the bytes from a file to a byte array. This method takes care of opening and closing the file for you. The readAllLines method reads all lines from a file to a list of strings. This method also takes care of opening and closing the file for you. The charset parameter specifies which character set should be used for decoding the file. Using charset.defaultCharset works best in most cases. Here you can see our earlier groceries example, but now worked out without streams but with the files class instead. You can see that the code is easy to read and follow. Two methods exist to write all bytes or lines to a file, as you can see here. By default, both methods create a new file or overwrite an existing file. The methods discussed so far are fine when you're dealing with small files. But when you need to work with large files, you cannot store the contents of the file in memory all at the same time. We already know how we would approach this problem using buffered character streams. The NIO2 API provides a clean way to read and write files using the following two methods. New buffered reader, which returns a buffered character stream to read a text file in an efficient manner using the given character set to decode, and new buffered writer, which returns a buffered character stream to write a text file in an efficient manner using the given character set to decode. This code fragment illustrates the new buffered reader method for our groceries example in combination with a try with resources block. Here you can see some methods listed to create files and directories. The create file method creates an empty file. The create temp file method creates a temporary file in the specified folder. The create directory method creates an empty directory. The create temp directory method creates a temporary directory in the specified folder. The new directory stream method lists all the contents of a directory. This example shows how to list the contents of a directory using the new directory stream method. The output can then be as displayed to the right. Note that if you would only be interested in txt, doc, or PDF files, you can invoke the method as follows. Files dot new directory stream dir, comma, txt, doc, PDF as illustrated. In what follows, we will illustrate a set of alternative recursive methods you can use to copy, move, delete, and search through directories, which you can easily reuse in case you would need it. The delete method is a recursive method to delete all files in a directory. The getFiles method returns all files and subdirectories in a given folder. However, since deletion will only work on empty folders, you want this method to first return all directories, followed by all files to ensure that the delete method first goes through all directories as far as possible. The copy method can be defined in a similar way as you can see here. The move method just reuses the copy and delete methods. The search method uses a path matcher object to match a file name to a provided input string. We now also include a main method to test all previous methods, as you can see illustrated here. Here you can see the corresponding output. Prior to the Java 7 release, the java.io.file class was the default mechanism used for file I.O. This class is still present for reasons of backward compatibility, but has several drawbacks such as the following. Some methods don't throw exceptions when an error occurs. Well-defined support for links is lacking. Accessing file metadata can be difficult and slow. Fetching information over a network introduces scalability issues, and some methods do not work consistently on various operating systems and platforms. As an example, the following code fragment shows how to loop over the contents of a directory using the legacy API. This particular example might appear simple compared to the corresponding NIO2 implementation, since fewer imports are used. However, keep in mind the other advantages of NIO2, such as reading and writing, for instance. Hence, the NIO2 approach remains the recommended one. We hereby conclude this chapter on basic input-output with Java and file input-output. You've seen what is meant by stream-based input-output, learned how to interact with users over the command line, and learned how to write and read content to and from files using both the NIO2 and legacy API. As always, don't be afraid to peruse the Java docs or explore the methods offered by Pat and Files and other classes using Eclipse's auto-suggest functionality. It's a great way to experiment and learn.